I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
We can only do so much with the angular quantities such as angular velocity and acceleration. Like we saw in the linear motion, the energy principle is very handy in solving a lot of problems. And there is similar method in the rotational motion. And let's have a look at that. So first of all, let's consider some lump of mass. Let's define in such a way that it consists of a collection of particles. So the kinetic energy of each of those particles is half times mv squared if it's going in some direction at velocity v. If this velocity happens to be along a rotational motion, so then we can say, as we learned, that the linear velocity is the multiple of angular velocity times the radius of curvature at that point. So for example, we would have radius of curvature here, and the motion would be along like a curved path like this. That's the thinking behind this. So then we can replace omega r for v, and we get half times m omega squared r squared. And if we think that we have a collection of these particles, so then each one of those particles has certain mass, a certain velocity, depending how far they are from the axis of rotation. So we add the same indices here, mass and radius. The angular velocity is same for all of them as it is for all rigid bodies. All the particles or the components have the same angular velocity, although they might have different linear velocity. Now, what we can do next is, of course, sum up all of these individual energies of the individual particles. And here we have it nicely written out. So first of all, here's particle 1, particle 2, and so on. And if we add them up, we get this expression here on the right. And we can rearrange this a little bit. So let's take the half first, and then the sum of, or the sum over the product of mass and the distance squared of each individual particle, like this. And we call this term the sum of m times r over all particles, the moment of inertia. And let's leave that aside for a while. So now we can just state the rotational kinetic energy, K, or we can call it Kr if you like, to be half times I omega squared, where I is the moment of inertia of that object and omega is the angular velocity. So it's strikingly similar to the definition of linear kinetic energy, half times mv squared. So let's have a better look at this moment of inertia. So first of all, it means, if you look at these formulations, that if we have a high or large moment of inertia, the object has large kinetic energy, which means that a lot of work has to be done to make it rotate at certain velocity. And also, if we want to slow it down, we need a lot of work to do that. And secondly, basically what the moment of inertia is, it is the distribution of mass in the object. if all of the mass was just in one particle or one lump mass, then we would see here that the moment of inertia for a particle, let's call, or a point mass better, it would be just, there's one object, mass m, distance r squared, so that would be just m r squared. So that's the upper limit for the moment of inertia of an object. And that is simply because all of the mass is as far away from the axis of rotation as possible. The application of this result that we got for rotational kinetic energy is pretty straightforward. It's done exactly in the same way as we did for linear motion, where the kinetic energy was just half times mv squared. And we'll see how to use this more in the examples. But for the rest of this video, let's concentrate on how do we, in general case, calculate the moment of inertia. Of course, it gets tricky for complicated objects, but we'll look at some simple ones. Let's start by evaluating the moment of inertia for a simple rod that has radius r and then some length L, like this. And by definition, the moment of inertia is the sum of all the individual particles multiplied by their distance from axis of rotation. And let's have our axis of rotation at the end of this rod. So that is squared. So basically, another way of saying this is that we take integral of this all over the whole object, and we sum all these individual tiny masses that are some distance r away from the axis of rotation. And how do we do it in this case? So what are we integrating over? So first we have to look at this mass here, dm. So mass is same as density times volume. So now we ask, if we know the density, what is the volume of this object? Or what is the volume of this infinitesimally small piece of the object? And we have to be clever about this before we go with integration. So this is a rod, so it makes sense to integrate over the length of it and analyze just thin slices of it, that they have some width dx, and of course the area of every slice is just the area of the rod at the end, so pi r squared. So in this case we can write the volume of this slice is the dx, the length times the volume, pi r squared. This was the integral over the whole volume of the object, and now we can rewrite it as, or write it in such a way. So first of all we have the r squared, and then we have the dm, the elementary or infinitesimal mass unit. So it's going to be rho pi r squared times dx. So like I said, we are integrating over the length of this rod, and hence we go from 0, let's say 0 is here, all the way to the other end, the length L. And let's take everything. Oh, okay, of course, if we call this dx, then the distance of this unit from the 0 is x as well, and we have to replace r squared, which is just a general distance. In our specific case we call it x because we're integrating along the x-axis like this. So now we can take the constant terms out and we get rho pi r squared and integral over the length of x squared dx. And we carry out the integration, so 0 to L x to the third over 3. And if you place the limits, so we only get L to the third minus 0, so rho times pi r squared L third divided by 3. So what does this tell us? So let's see what we have here, in fact. So that's the area of the rod at the end. If we multiply that by one of the L's, so we get rho a L times, and then we have L squared over 3. Then we have volume here, and rho times volume is mass. So we have the mass of the whole object times L squared over 3. And that is in fact is the moment of inertia of this rod about the axis that goes through one of the ends. First of all, we see that this is indeed smaller than the maximum possible value. So if all of the mass would have been at the other end, then the moment of inertia would just be m times L squared, but it is in fact only a third of that. And the moment of inertia depends, of course, where do we take this rotation axis to be. In this case, what was at the end. But what if we wanted to, for example, calculate the moment of inertia through an axis that goes through the center of mass of this object, that is straight in the middle? We could do this same procedure integrating both ways, but in fact there's a shortcut, and that is called the parallel axis theorem. It states the following: the moment of inertia about any axis parallel to the axis of rotation that goes through the center of mass is the moment of inertia through the center of mass plus the mass of the object and then the distance between these two axes. So in this case, the distance, if we want, okay, let's put it this way. So first of all, we calculated the moment of inertia about some other point P. So here we have our moment of inertia would be about this axis would be IP. And we wanted to calculate the one through the center of mass. So here's our I center of mass. The distance between these two axes, first of all, they're being parallel, as we see, is here. So that's only, or that is L over 2, half of the length. And now we can go about this and in fact calculate the moment of inertia through center of mass by using this formula. So what we get is IP minus m times d squared. And moment of inertia IP is what we had here about this parallel axis. So that was 1/3 ml squared, and then we have to subtract the mass times the distance squared. So that's going to be L over 2 squared. So we get, let's continue this way, 1/3 ml squared minus, so that's going to be only 1/4, so 1/4 ml squared. And we have to make the denominators the same, so we multiply this by 4 to get 4 over 12 ml squared, and here we by 3, so we get 3 over 12 ml squared, and that is just 1/12 over ml squared. And as we see, the moment of inertia about the center of mass is even smaller, and it's always smallest about the center of mass, as we can always also see from this formulation. So if you go about some other axis, it always adds something into it. I'm making a bit of a mess here, but I wanted to bring this chart up. So here we have moments of inertia for different typical geometries. So we have sphere, hollow sphere, different kind of cylinders, flat plates, and here we have the slender rod that we just evaluated. And this is the where the axis is through one end, as it says here. So that's 1/3 ml squared what we got here. And then the same thing for when the axis of rotation goes through the center. So 1/12 ml squared. Equipped with this expression, half times I omega squared, and means of evaluating the moment of inertia, either by calculating or looking it up from a table, we are ready to apply the principle of rotational kinetic energy to a variety of problems, including or involving rotational motion.